you non-multiway cut and subset fit by Vertex set on graphs of bounded Mim-width. So this is a joint work with Karis Papadopoulos and Yarnan Hotel. In this talk, I will not only focus on Mim-width because we have results also on rank width, and I will start by presenting these two parameters. Let's start with something you all know, tree width. So tree width is wonderful in so many ways. It has plenty of algorithmic application and structural properties, and we know a good algorithm to compute tree width in FPT time. So why do we need these two other parameters? And the thing is, dense graph classes can not have bounded tree width. But these dense graph classes can be simple. This is the case for interval graph, permutation graphs, and cographs. And sometimes the simplicity of these dense graph classes and the tractability results we have on them can be explained with rank width and Mim-width. So that's for the motivation. Now let's talk about the definition. And all of these parameters are based on the same idea. So we take a graph and we recursively decompose this graph. And for rank width and Mim-width, we take the vertex set and we divide it into two parts recursively. And we do it in such a way that all the cuts of this decomposition are sample. And we describe the simplicity of a cut with a function that takes a cut and returns a number. A small number means a sample cut. And of course, there is different notion of simplicity. There is different function to measure the simplicity. And this gives different width measures. So the width of decomposition is the maximum of this function among all the cuts of a decomposition. And the width of a graph is the minimum width among all the decomposition of this graph. And to define rank width, we take the function that takes a cut, A, B, and returns the rank of the adjacency matrix between A and B over the binary field. So in this case, so for this cut, we have this adjacency matrix, and the rank of this cut is 2 because this matrix has rank 2. Right, now for Mim-width. So for Mim-width, we take a different function. So we take the function that takes a cut AB and returns the size of a maximum induced matching in the bipartite graph between A and B. So this is a maximum induced matching of this cut. So you can see that this cut has Mim-width 2. So that's for the definition. So these parameters induce the following hierarchy. So this arrow here means that if a graph has bounded tree width, then it has bounded rank width. And this diagram represents this relation between these parameters. So you can see that click width and rank width are equivalent, and Mim-width is bounded in strictly more classes than the other parameters. On the left, you have the modeling power, what we call the modeling power. This is the graph classes where these parameters are bounded. So for example, trees have bounded tree width, cographs have bounded click width, and for Mim-width, interval graph, permutation graph, and all of these graph classes have bounded Mim-width. On the right, you have some meta-algorithmic application of these parameters. So for tree width, we have Courcell's theorem that say that every property, every MSO2 property is checkable in FPT time, parameterized by the tree width and the length of the formula. For rank width and click width, we have a variant of this theorem on a less powerful logic. And for Mim-width, we don't have anything so general, but we have some result on some smaller class of problems. And you can see that there is a trade-off between the modeling power and the algorithmic application. For the computation, so for all of these parameters, it is NPR to compute them. But for tree width and rank width, we know efficient algorithm, efficient FPT algorithm to compute them, and they have this running time. For Mim-width, there is plenty of open questions there, and we just know that it is unlikely to be FPT, but we don't know if it is XP or not. So now I will talk about the main problem we are interested in. This is subset feedback vertex set. And I will start by talking about feedback vertex set. So we are given a graph and we want to find a set of vertices of minimum weight that hits all the cycle of this graph. So when we remove this set of vertices, the resulting graph is a forest. And in subset feedback vertex set, we are given a graph, but also a set of vertices that we will call S. And we want to find a set of vertices of minimum weight that hits all the cycles that go through S. So in this example, so this is S, and the vertices of S will always be white filled, this talk. And it is sufficient to remove these two vertices. So this is the solution of the problem, because when we remove these two vertices, you can see that there is no cycle that use these two remaining vertices. Possible under ETH for subset feedback vertex set, because we proved recently this lower bound. On the positive side, we know that subset feedback vertex set is solvable in polynomial time on interval graphs and permutation graphs, so two graph classes of bounded Mim-width. And for feedback vertex set, we know that we can solve it in this running time. So here Mim is the Mim-width of a given decomposition, and n is the number of vertices of the input graph. So this was proved in two different ways. And with these two results, it is quite natural to ask, can we do the same for subset feedback vertex set? And the answer is yes, but with a slightly worse running time. And this is the main result of this talk. So we prove that subset feedback vertex set is solvable in this running time, and we always assume that we are given a decomposition. This is not the only result we have on subset feedback vertex set. So we prove also that we can solve this problem in polynomial time on interval graphs, permutation graphs, and all of these graph classes, the same algorithm. And this is a consequence of Mim-width algorithm, because on these graph classes we can compute a function of bounded Mim-width time. For rank width, we prove that we can solve this problem in this running time. And this is the first algorithm for the problem. And also first algorithm with a single exponential time. And this is because before we knew that subset feedback vertex set was FPT, parameterized by rank width, but because we can formulate it in SO1, and we use a variant of Courcelles theorem. So the algorithm we get from this theorem is running time with a exponential tower. And all of these results, so the Mim-width algorithm, the result on the graph classes, and the result rank width, holds also for a problem called node multi-way cut, because we can reduce this problem to the feedback vertex set with a very simple reduction. I will talk about this problem and this reduction later. So now I will present to you our algorithm for Mim-width and subset feedback vertex set. And we use this equivalence relation called one neighbor equivalence. And this relation is defined through a cut. So here the cut is AB, and we say that two subsets of A are one neighbor equivalent over A if the subset have the same neighborhood in B. So in this example, X and Y are equivalent, they have the same neighborhood in B. We denote by nec1 of A the number of equivalence classes over A in this talk. And we can use this equivalence relation with Mim-width because we have this upper bound on the number of equivalence classes. And you can see that this is not a 1, this is a 2, and this is not a typo. So in fact, we use equivalence classes where we don't require that the two subsets have the same neighborhood in B. We require something stronger. But I will not talk about this equivalence relation because it is more complicated to define, and we will not see why we use this stronger equivalence class relation. So just remember that when I say that two subsets are equivalent over A, then they have the same neighborhood in B, and we use also this relation over B. So I will say that two subsets are equivalent over B. Two subsets of B are equivalent over B if they have the same neighborhood in A. So we prove this very important result, and it is very important because from this result we deduced the algorithm for subset Fibonacci Vertex set. The rest of the proof is just basic dynamic programming. What is this result telling us is for each cut AB, it is sufficient to keep this amount of partial solution. So here, neg2 of A and neg2 of B are the number of equivalence classes of the relation I was talking about in the previous slide. And so there is, to explain this lemma, we can just say, okay, you have a set of partial solutions. So you have freshly computed this set of partial solution. And C, so we call it C. And there exists an algorithm that outputs a subset of C, D, such that the size of D is small, so upper bound by this, and D is equivalent to C. And equivalent here means that for every Y in B, the best solution we get from C and Y has the same weight as the best solution we can get from D and Y. Our algorithm will not try to find directly a minimum subset Fibonacci vertex set. Instead, it will try to find the maximum complement of subset Fibonacci vertex set. We call these complements S forest. And S forest are graphs with no cycle going through S. So this is an example of S forest. Recall that the white field vertices are the vertices in S. And what you can see in this example is that when you take the connected component induced by the vertices that are not in S, so the connected component in blue here, and you contract them, what you obtain is a forest. And these contractions and this relation between forest and S forest is very useful in our algorithm because it allows us to use the IDs for Fibonacci vertex set to solve subset Fibonacci vertex set. And this is what we will do. What we prove is that given a S forest induced by subset X of A and subset Y of B, we can do these contractions on each side such that we obtain a forest at the end. And for X, what we contract are the connected components induced by the vertices in X that are not in S. But we cannot do the same for Y. We have to contract more. So here, for example, we have this cycle, but we can contract these two guys to obtain a forest. So in Y, we have multiple choice for the contractions, but for on this side, we have only one choice for each partial solution. And this is fine because we are dealing only with this side. So for each partial solution, we have only one contraction. What we prove is that after these contractions, in the graph, bipartite graph between this side and this side, we have a vertex cover of size at most 4 times the Mim-width, and all the vertices of this vertex cover are different neighborhoods in this bipartite graph. And it means that they are not equivalent under the two neighbor equivalence. So now we are ready to define what we call indices. So an index is a collection of at most 4 times the Mim-width plus 1 representatives for the two neighbor equivalence over A and B. And these representatives, so some of them represent the vertices of the vertex cover. And we differentiate those that belong to S and those that do not belong to S. And we also have one representative on this side that represents the vertices in X that do not belong to the vertex cover. And the number of indices is at most is upper bound by this. So this is the bottleneck of our algorithm. So now we associate each index with some partial solution and some subset of B. For the partial solution, we say that X is associated with I if after the contraction we can map each representative of the vertex cover to some vertex in X, and the remaining vertices, those that are not mapped to the vertex cover, are equivalent to this orange representative. And we also require that the graph induced by the representative on this side and x is a forest. On the other side, we say that a subset y is associated with I if we can construct y in some way such that we can map the representative of the vertex cover to some vertex here. And we keep also the information that, oh, this vertex is in S, so this vertex should be in S. And we require also that the vertices that are not mapped to the vertex cover, that they have no neighbors in the representative, the orange representative here. So we prove that for every solution, there exists an index such that the part of this solution in A and the part of this solution in B are associated with I. So every solution is associated with at least one index. And this is very useful because now we can define this equivalence relation. So for the partial solution and for each index. So we say that two partial solutions x and w associated with an index I are I equivalent if they connect the vertices of the vertex cover in the same way. So here the vertex cover, it is the vertex cover described by I. And since this vertex cover has at most 4 times the Mim-width vertices, we can upper bound the number of equivalence classes with this. And what we prove next is that if two partial solutions are E equivalent, then for every Y associated with I, X union Y is a solution if W union Y is also a solution. So there is an equivalence between partial solution, and we prove that it is sufficient to keep for every index I a partial solution of maximum weight for each I equivalence class. And so the number of partial solutions we keep is at most this amount. So this is the number of index, and this is an upper bound of the number of E equivalence classes. This is upper bound by the running time of our algorithm. And this proves the theorem for Mim-width. For rank-width, we deduce the algorithm from these two upper bounds. So this is the upper bound on the number of two neighbor equivalence classes. So we have this upper bound, and we also know that the Mim-width of decomposition is at most the rank-width of this decomposition. And from this upper bound, we deduce that this amount is upper bound by this, and this gives us the algorithm for rank-width. Now, for node Multiway cut. So in this problem, we are given a graph and a set of vertices T, and we want to find a subset of vertices of minimum weight that disconnect all the vertices in T. So for example, when we remove this vertex set, we disconnect all the vertices in T. And we can reduce this problem to subset feedback vertex set by adding just one vertex, and we make this new vertex adjacent to all the vertices in T. And you can see that now a cycle using this new vertex implies that there is a path between two vertices in T. So we put this vertex in S, and then we have a reduction from node Multiway cut to subset feedback vertex set. And so we can use the algorithm for subset feedback vertex set to solve node Multiway cut, and we have this theorem. So now it's time to conclude. We have so now you know that this relation to neighbor equivalence and the other relations related to this one are very useful, and in fact they can use for many problems. So it was used for sigma row dominating set problems. So this is a family of problems based on local constraints. And it was also used for the connected and acyclic variant of these problems, and also max cut. And we show that this is useful also for subset feedback vertex set and node Multiway cut. And this is nice for many parameters. We can construct with this equivalence relation many algorithms for many parameters, for tree width, click width, rank width, Q rank width, so a variant of rank width and Mim-width. And just a word. So our algorithm is the first one to use indices where the number of representatives is not constant, and this is quite interesting. Now some open questions. So the first one is about the meta-algorithmic application of Mim-width, and ask for can we characterize the family of problems that are XP parameterized by Mim-width of a given decomposition. So this was partially answered already by some results, and in particular this one. And the second question is about the computation of Mim-width, and so can we approximate or compute the Mim-width of a graph in XP time? I recall that it is unlikely to be FPT, is proven. And one step to ask this question would be to answer this question would be to recognize the graphs of Mim-width1. Now this is the end of this talk. Thank you for listening. Now it's time for the questions.